the polar covalent bond. Alright, I said the polar covalent bond. Okay. How will I explain this one? Alright. First and foremost, I will explain what a covalent bond is. Let's break it back up. Polar, then covalent bond. Right? Now, let's speak a covalent bond. What is a covalent bond? Then we join all of them together. Right? Now, a covalent bond is a bond altogether. Is a bond that is formed when two atoms share electron. Two atoms when they share electron. When they share electron, they form what we call the covalent bond. Altogether, yes. And the reason why they share electron is for them to become stable. Yes, they have purpose. The purpose why they share electrons for them to become stable. Alright. Now moving further. Now, what is a covalent bond? A polar covalent bond. Alright. In many covalent bond, right? I've explained what a covalent bond is, right? That is a bond from when two atoms share electron. And the reason why they share electron is for them to maintain stability, right? Now, let me explain what a covalent bond is. Alright, know that in many covalent bonds, right, the electrons are not equally shared between the two bonded atoms. Let's get it right. I want to explain what a covalent bond is, what a polar covalent bond is. You know that in many covalent bonds, the electrons are not shared. They are not shared equally. They are not shared equally between the bonded. They are not shared equally between the bonded atoms. Let's get to this point. Right. I said in many covalent bonds, the electrons, they are not shared equally between the two bonded atoms. When this happens, this is what we call the polar covalent bond. That is, when it happens, it forms what we call the polar covalent bond. What I'm saying here in essence is that the polar covalent bond is just like a covalent bond in which the electrons are not equally shared between the two bonded atoms. Let's get it right. That is what a polar covalent bond is. That is a covalent bond where electrons are not shared. The electrons are not shared or are shared unequally. Let's get it right. Now let's take a good example. Let's take a good example from our slide there, using hydrogen chloride. It says here, right? The hydrogen chloride. You know that hydrogen chloride, right? It's dissolved in water. When it dissolves in water, it's from hydrogen ion plus chloride, right? And chloride, right? That is in its gaseous form. Altogether, yes, in its gaseous form. When it dissolves, it forms the hydrogen ion and the chloride, right? But its pure state, that is, which is gaseous, but in its pure state, it is a covalent compound. Altogether, that is, in its pure state, pure is here.
It's a covalent compound. Now, what happened in the HCl bond, that is the hydrogen chloride bond, is that the electron, they are unevenly distributed altogether. Yes, the electron, they are unevenly, they are not equally shared. Yeah, they are unevenly distributed between the hydrogen and the chloride and the chlorine altogether, and they are pulled towards the chlorine and away from the hydrogen. We're together, right? Yes, that is the explanation of a polar covalent bond. You guys said that a polar covalent bond is simply a covalent bond where electrons are shared unevenly. Yes, that is, they are not shared equally. Then we take a good example of hydrogen chloride, right? And I said that in hydrogen chloride, the electrons, they are unevenly distributed between the hydrogen atom and the chlorine atom altogether. And in this distribution, the electrons, they are pulled towards the chlorine side altogether. They are pulled towards the chlorine, that is the electron, they are pulled towards, that is the bond that is the bond that is between the hydrogen and chlorine. It is pulled. Let's say this is the bond, right, between hydrogen and chlorine altogether. This is the bond between hydrogen and chlorine. The bond is pulled towards the chlorine side and away from the hydrogen side. This means that the bond is polarized. So a bond in which electrons are shared unevenly is called a polar bond altogether. A bond in which electrons are shared unequally, it's called a polar bond. So therefore, hydrogen chloride, since the electrons, they are shared unequally, because the bond moves towards the chlorine side and away from the hydrogen side. Since the bonds shared, they are unequally, so therefore hydrogen chloride is a polar covalent bond altogether. So therefore hydrogen chloride is a polar covalent bond. Now I know the question that will be running through your mind is that, what does this unequal sharing cause? Like, what is the effect of this unequal sharing of electrons? That is the unequal sharing of the bond, which normally happens in polar covalent bond. Because we said that a polar covalent bond is a bond in which the bond, they are being shared unequally between the two bonded atoms. Now, I know the question that will be running through your mind is that, what does this unequal sharing really cause? Let me wipe my board so that we'll explain what is the effect of this unevenly shared electron. I said, what does this unequal sharing really cause? Using the previous example that we used, which I going to use hydrogen chloride, right? I said that in hydrogen and chlorine, the bond moves towards the chlorine side and away from the hydrogen side altogether. Now, because the electron moves towards the chlorine altogether, because it moves the bond or the electron, it moves towards the chlorine, right? Because it moves towards the chlorine side, the hydrogen altogether, the hydrogen becomes slightly positive. Yes, it becomes slightly positive. Why the chlorine, since the electron or the bond moves towards the chlorine side, the chlorine becomes slightly negative. Are we together? I said, what does this unequal sharing that occur in polar covalent bond, what it really causes is that, using the example of hydrogen chloride, we said that the electron or the bond, it moves towards the chlorine side and away from the hydrogen side. Since it moves towards the chlorine side, the hydrogen atom becomes slightly positive, while the chlorine atom becomes slightly negative. So, in essence, the hydrogen chloride molecule, altogether, the hydrogen chloride molecule now has two ends. Yes, the hydrogen chloride molecule now has two ends, which is a positive end and a negative end. Yes, it now has two ends, which is a positive end, and let me change my pen, and a negative end. Yes, and this is what we call dipole. Please take note of this. Are we together? I said that what does this unequal sharing of electron, which happens in polar covalent bond, what it really causes is that it causes one of the atoms to become slightly positive and the other atom to be slightly negative. Are we together? Now we use the example of hydrogen chloride. We said that in hydrogen chloride, the electron or the bond moves towards the chlorine side, which makes the hydrogen become slightly positive and the chlorine to become slightly negative. Now in essence, the hydrogen chloride molecule now has two ends, a positive end and a negative end, and this is what we call the dipole. We are together, right? And this is what we call the dipole. Now the dipole is what we use to measure how polar a bond is. We're together, right? Yes, the dipole, that is the two ends, right? The positive end and the negative end of a molecule. That's what we use to measure how polar a bond is. All together, the dipole is what we use to measure how polar a bond is. We are together, right? Yes, that's what we use to measure how polar a bond is. And also there is something we call the dipole moment. Yes, from your slide. There's what we call the dipole moment. You understand now what the dipole is, what we use to measure how polar a bond is, right? That is the positive end and the negative end, right? That's what form the dipole. Let's get right. That's what form the dipole, and the positive and the negative end is as a result of shared electron that is unevenly distributed. That is, they are not shared equally. That is what gives rise to the dipole, right? Which is the positive and negative end. Are we together? Now, I said there is what we call the dipole moment, and it is being represented with this sign. Yes, from your handout, which is mu, the dipole moment, and it is measured in a unit called the dive. Yes, the dive, which is D. But together, I would like you guys to also take note of the points. Yes, and it's also measured in a unit called the dive. We are together. So in essence, hydrogen chloride, it has a dipole moment of hydrogen chloride, which is a polar bond. It has a dipole moment of 1.08 D. That's good, right? I said that the dipole is what we use to measure how polar a bond is. That's good, right? And we said that there is what we call the dipole moment, right? There's what we call the dipole moment. That is what we use to measure how polar a bond is, right? The dipole or the dipole moment. That's what we use to measure how polar a bond is. Right, and its unit it's in Dipole, and we said that hydrogen chloride has a dipole moment of 1.08 D. Right, together, right? Then in hydrogen gas, which is different. You know, hydrogen gas is, yes, it's hydrogen, which is a gas, right? It's a gaseous element. You know that hydrogen chloride is a molecule, right? In hydrogen gas, where in hydrogen gas the electron, they are evenly shared. Yes, this one join with this, they are evenly shared. That is, hydrogen gas is not a polar covalent bond, because one of the way you get to find out if a compound is a polar covalent bond is that the electron or the shared bond, they are shared unequally. In hydrogen gas, the electron, they are shared equally. So therefore, since the electron they are shared equally, its dipole moment, let me change my pen, its dipole moment, that is in hydrogen gas is 0 altogether. Why I said that the dipole moment in hydrochloric acid is 1.0 D. The reason why it has a dipole moment because they are polar covalent bond. Are we together? Alright, now from your outline here, the dipole moment is given by a formula. Let me wipe my board so I'll write the formula. Right, I said that the dipole moment is given by a formula, right? Which is dipole moment. It is being represented by this symbol mu equals to Q multiplied by R, where Q is the amount of separated charge, and R is the distance between the charges. Altogether, I said that the dipole moment is being given by a formula mathematically mu equals to Q multiplied by R. Yes, where your Q is the amount of separated charge and your R is the distance between the charges. Now, one important thing I want you guys to note about the dipole moment is that the dipole, it has a direction. Please take note of this. Yes, the dipole, it has a direction. It has a direction. Are we together? That is, the dipole, it has a direction. It moves from the positive end to the negative end. From the positive end to the negative end. That's why I said it has a direction. So therefore, in hydrogen chloride, it will therefore move from the hydrogen, right? Yes, it will move from the hydrogen, which is positive, right? Which is the positive end, to chlorine, which is the negative end. I said that the dipole moment is given by formula Q multiplied by R, where Q is the amount of separated charges, R the distance between the charges. And I said that I want you guys to note one important thing is that the dipole has a direction, and it usually moves from the positive end to the negative end. So therefore, in hydrogen chloride, which is a polar covalent bond, the dipole moves from hydrogen to chlorine, which is the negative end. We are together, right? Yes, which is the negative end. Now, there's one other important thing I want you guys to take note of here is that the strength of polarity, that is, the strength of a polar covalent bond, depend on two things. The strength, let me write it. The strength of polarity, that is, the strength of polar covalent bond, it depends on two things. Number one, which is the amount of charge separated, which is the Q, right? Yeah, the strength of polarity, that is, the strength of a polar covalent bond, depends on two things: the amount of charge separated, which is Q, the amount of separated charge, which is your Q, right? And also the distance between them, which is R. Please take note of this. The strength of a polar covalent bond, it depends on two things. It depends on two things: the amount of separated charge, which is the Q, and the distance between these two charges, between the charges. Are we together? Yes, that is what determines the strength of a polar covalent bond, or the strength of polarity. Okay, now let's talk about molecule in general, right? Now, molecule with dipole moment, molecule which have a dipole moment, they are called polar molecules. Altogether, yes, they are molecules. From your slide there, molecule with dipole moment, they are called polar molecule. An example is the hydrogen chloride. Altogether, then molecule without dipole moment. Those without dipole moment, they are called non-polar molecule. Non-polar molecule. An example is the hydrogen molecule. Altogether, and also there's also one key thing I want you guys to know is that some molecules even have more than one polar bond. Altogether, yes, some molecules they have more than one polar bond. So molecules they have more than one polar bond, and such molecules they are termed a bond dipole. Please take note of it. Let me underline it with white. Yes, I said that some molecules they even have more than one polar bond, and each bond contributes its own dipole. Altogether, yes, each bond contributes its own dipole, and such molecules they are called the bond dipole. Altogether, all right. One last thing for you to call a compound, or for you to call an atom, or a molecule a polar covalent bond, that is a molecule that contain dipole, or for you to call a molecule that it has a polar covalent bond, it is in its term of electronegativity. Altogether, yes, because covalent bond they are generally considered polar if the difference in their electronegativity, that is, if the differences in their electronegative value is between the atom is about, let me wipe this board. What I mean here is that is in terms of negativity, right? Let me write it. In terms of negativity, a compound is considered a polar covalent bond if the differences in the electronegativity between the atom, if the differences between the electronegativity between the atoms is between, please take note of this, between 0.5 and 1.9. Anything more than this, that compound is not a polar covalent, does not contain a polar covalent bond. Altogether, yes, that is how you get to know if a compound contains a polar covalent bond or not in terms of electronegativity. The differences in the electronegativity between the atom ought to be between 0.5 and 1.9. So in essence, polar covalent bond is when two atoms are shared. That is, in summary, a polar covalent bond is when two atoms are shared unequally. Please take note of it. That is the summary of everything. Where two atoms they are shared unequally. Making one end, when they are shared unequally, making one end slightly positive and the other end slightly negative. Yes, and the other end slightly negative, making one end slightly positive and the other end slightly negative. And because of the positive and negative end, a dipole is formed. Are we together? Yes, because of this, a dipole is being formed. Because of this positive and negative end, a dipole is being formed. Are we together? Yeah, a dipole is being formed. And now we measure dipole using what we call the dipole moment, right? Which I wrote that the dipole moment, it is being given by mu q multiplied by r, right? Yes. And finally, I said molecules that have dipole, they are called polar molecules, while those that do not have dipole, they are called non-polar molecules. With this, we've come to the end of polar covalent bond. Now let's move to our next slide. Alright, now let's look at the factor influencing organic chemistry. So when you study organic chemistry, you get to notice that some reactions they happen easily, while some they are slow or even difficult to happen. You understand? When you study organic chemistry very well, you get to find out that some reactions happen very easily, while some they are slow or very difficult. Yes, or very difficult to happen, or very difficult. And the reason being that reaction they are mostly influenced by certain factor. Altogether, yes. The rate at which a reaction occur, either being it fast or slow, they are influenced by certain factor, and these factors they are mainly of two types. Yeah, there are two types. The factor that influence organic reaction, they are mainly of two types, which are, we have the electronic factors. Altogether, yes, which are the electronic factor and steric factor. Please take note of this, because when you study organic chemistry very well, you get to understand that some reactions happen very fast, while some they happen at a slower rate, and even some that are very difficult. The reason being that they are being influenced by certain factor, and these factors they are mainly grouped into two, which are the electronic factor and the steric factor. Now from your outline, now let's focus on the electronic factor. Altogether, now let's move to one of the electronic factors which influence organic reaction from your outline, which is the number one, the inductive effect. Altogether, the inductive effect, these are electronic factors. Altogether, alright. Now the inductive effect, it happens when atom in a molecule pull or push electrons through the sigma bond. Please take note of this. Altogether, I said that I'll make it very simple. The inductive effect, it happens when atoms in a molecule, it happens when atoms in a molecule pull or push electrons through a sigma bond. You know what is sigma bond, you know what is a pi bond, right? Alright. The inductive effect, it happens altogether. We said that factor influencing organic reaction, for organic reaction to occur under the electronic effect, we have the inductive effect. I said that in the inductive effect, it happens, that is, the effect takes place, that is, the effect is being felt when an atom in a molecule pull or push electron through the sigma bond. We are together, right? Now let me make it very simple for you to understand now. When carbon is bonded to a more electronegative atom, let's say carbon is bonded, when carbon is bonded to a more, let me use the example to explain, to a more electronegative atom, let's say like chlorine, let's use chlorine. Yes, are we together? When carbon is bonded to a more electronegative atom like chlorine, that atom attracts electrons towards itself. Are we together? Yes. When carbon is bonded to a more electronegative atom like chlorine, right? This the chlorine atom attracts electron towards itself. That is the shared electron, right? Toward itself. It attracts the shared electron toward itself. So the bond become unequal. Let me write it. So the bond become unequal. It becomes unequal. Are we together? I said in inductive effect, it happens when an atom in a molecule pull or push electron through the sigma bond. Then I cite an example using carbon. When carbon is being bonded by a more electronegative atom, use chlorine for instance. The chlorine atom attracts electrons toward itself, so the bond become
unequal. Are we together? Are we together, right? And this is an example of inductive effect because the chlorine atom attracts the electron towards itself, thereby making the bond unequal. Are we together? All right. Now let me draw something to explain it further using the carbon and chlorine. Let me wipe the board so you understand what I'm saying properly. Okay, I said that the chlorine atom, right, it push electron towards itself. Are we together? That is, in essence, let's say I said if carbon is bonded by a more electronegative atom like chlorine, right? I said that chlorine pull electron more strongly, that is towards itself, right? It pull electron more strongly. Then as it pull electron towards itself, the carbon becomes slightly negative. If you remember from our dipole moment, right? Yes, the carbon becomes slightly positive. The carbon becomes slightly positive, and this shift of electron through the bond, this is what we call the inductive effect. Are we together? Yes, the shift of electron through the bond, the shift of electron through the bond is what we call the inductive effect. We are together to this point. I said that the inductive effect is occur when atom in the molecule pull or push electron through the sigma bond, right? I said that let's use an example using carbon and chlorine. When carbon is being bonded by a more electronegative atom, like using chlorine for instance, the chlorine atom attracts the electron towards itself, thereby making the bond unequal. Are we together? As the chlorine pulls the electron towards itself, the carbon becomes slightly positive. Are we together? And this shift of electron through the bond, this is what we call the inductive effect. And also another thing I want you guys to note about the inductive effect is that, okay, it's not being captured in your slide, is that we have two types of inductive effect. How together? From this you get to find out that we have two types of inductive effect. The negative inductive effect, how together, that is the electron withdrawing group, right? Yeah, the electron that is pulling right towards itself. Let me name it as the withdrawing group. Yes, the withdrawing group. And we have the positive inductive effect, which is the electron donating group, right? Yes, let me name it as the donating group. Okay, let me clean the words so I'll write it properly. I said we have two types of inductive effect. We have the negative inductive effect, which is the withdrawing group. And the positive inductive effect, which is the donating group. All right, now let me explain the negative inductive effect. All right, let me write it. Number one, the negative inductive effect. All right, you get to understand that there are some atom or group of atoms that are very, very good at pulling electrons towards themselves. Using the example that I gave using carbon and chlorine, you get to find out that chlorine is a very good example of an atom which is very, very good at pulling. They are very, very good at pulling. Electron. They are very, very good at pulling electron towards themselves. That is the negative inductive effect. They are very good at pulling electrons towards themselves. And a very good example are atom or group of atoms that are highly electronegative. Yes, the example of atoms that have negative inductive effect. A very good example are atom or group that are highly electronegative. They are highly electronegative. Altogether, a very good example are atom or group of atoms that are very highly electronegative, like chlorine. Yes, chlorine is very electronegative. Even the fluorine is also very electronegative. Altogether, yes. We said that the negative or withdrawing group, they are atoms that are very good at pulling electrons from the cell. And now another important thing I want you guys to note about the negative inductive effect is that what do they actually cause? That is, what do they actually do in a molecule? Their effects. Altogether, what did they actually do? Let me write it now. Their effects. What do they actually do in a molecule? Now, you know that when electrons are pulled away from carbon, using the carbon that we gave, right? When electrons are pulled away from carbon become electron deficient. Very true. Altogether, that is the effect of negative inductive effect, is that, you know, when electrons are pulled away from carbon become deficit. It become electron deficit. That is why you see the carbon we have, it will be slightly positive. Altogether, yes, it will be slightly positive, right? It become electron deficit. And also, since carbon is now electron deficit, right, carbon become very easily attacked by electron rich species. Please take note of this. That is the effect of negative inductive effect. Let's go to our slide. Okay, yes, all right, this slide explains what I'm saying, right? It explains what I'm saying in detail. I said that carbon become electron deficit. That is the number one effect of the negative inductive effect. Carbon becomes electron deficit. That's the first thing that happened to carbon. Electron deficit. That's what happened to carbon. And since carbon is now electron deficit, carbon become easily attacked by electron rich species. Attacked by electron rich species. What is happening to my marker? Rich species, which are called nucleophile, right? Which are also called the nucleophile. Altogether, I said that what really happens, that is the effect of the negative inductive effect, is that they causes carbon to be electron deficit. That is making carbon to become slightly positive, right? Yeah, slightly positive and slightly positive. And also carbon become easily attacked by electron rich species called the nucleophile. Altogether, yes, carbon become easily attacked by electron rich species called the nucleophile. And also, one other important thing I want you guys to note here of the effect of the negative inductive effect is that it make nearby hydrogen atom easier to remove. Please take note, to remove during elimination reaction. Altogether, like it make the third effect of this negative inductive effect is that it make nearby hydrogen atom attached to carbon to be easily removed during elimination reaction, which is the removal of hydrogen. That is doing either dehydrogenation. Altogether, it makes, please take note of it, it makes hydrogen atom easier to remove. It made hydrogen atom easier to remove during elimination reaction. To be removed during elimination reaction.
Right, together now. This is one of the effects of the negative inductive effect. That is the electron withdrawing group. That is the group that are very good at pulling electrons towards themselves. Now let's move to the other type of inductive effect. Let me use a blue pen, which is the positive, right? The positive inductive effect, or the electron donating group. Yeah, the electron donating group. Donating, wow. Donating group. The electron donating group. The electron donating group, they show a positive inductive effect altogether, and some group, and this group, right, and this group of inductive effects, they act opposite. Yeah, they act opposite of the withdrawing group, the electron withdrawing group. What they actually do here is that they push electron towards carbon altogether. They push electron, that is, they do the opposite of the electron withdrawing group, right? The electron donating group, or the positive inductive effect, that is, the electron donating group, which show a positive inductive effect, they do the opposite of the electron withdrawing group, which shows a negative inductive effect. Is that this positive, they push electron towards carbon. Please take note of this. They push electron towards carbon. They push electron towards carbon, and also this group, they are called the electron donating group, right? Since they push electron towards carbon, and also they show a positive inductive effect. And a very good example of this group I want you guys to take note is the alkali group. Yes, there is a very good example of positive inductive effect. That is electron donating group. That is group of atoms that show positive inductive effect is the alkyl group. Alkyl group, like the likes of the methyl, which is CH3, right? Yes, ethyl, which is CH2H5, right? Yes, it's the alkyl group altogether. And also, one important thing I want you guys to note about the positive inductive effect is that to remember is that the when it comes to the strength, right? Because when it comes to the strength of the positive inductive effect, their strength varies. Yes, that's what I want to point it out. Their strength varies even when it comes to the negative. Even when it comes to the negative inductive effect, when it comes to their strength, it varies, right? The higher the electronegativity, the higher the strength of the electron withdrawing group, right? The lower the electron negativity, the lower the strength of its pulling of electron towards itself. When it comes to the negative inductive effect. Now also when it comes to the tertiary, the positive inductive effect, that is the electron donating group, their strength, that is the positive inductive effect strength, it's of different categories, right? Because I said that a common example of atom or group with positive inductive effect is the alkyl group, right? Now when it comes to their strength, the tertiary alkyl group are the strongest donor. Please take note of this. The tertiary alkyl group, they are the strongest. Then the secondary, then followed by the secondary, then followed by the primary, which is the weakest altogether. Yes, so that is the order, that is from tertiary down to secondary down to primary. They're together now. Now let's talk about the effect. That is, what does this positive inductive effect actually do, or actually does in a molecule? Let me wipe my board so I will explain. Okay, what they actually do, that is the positive. Let me write the positive inductive effect. What they actually does in molecule. What they actually does in molecule is that what they actually does in molecule when it comes to carbon. It make carbon, right? Number one, it make carbon to become electron rich. You know the negative make carbon to be electron deficient, right? But for the positive, it make carbon to be electron rich. Make carbon to be electron rich, that is slightly negative. While for the negative, it make carbon to be slightly positive, right? They are slightly negative. Make carbon to be electron rich, and also because it make carbon to be electron rich, then carbon has the tendency of repelling altogether. Yes, that is, you know that and that's why I said that the positive is the opposite of the negative. What happens in the negative is just what happened in the negative is an opposite, is just opposite is what is happening in the positive inductive effect, right? And since since the positive inductive effect, it made carbon electron rich, so therefore carbon will repel altogether. Yes, carbon will repel electron rich species. Yes, carbon will repel electron rich species, and also it also make hydrogen atom very harder to remove, which is opposite, right? It make hydrogen atom H2 very hard to remove, very harder to remove. So in essence, what I'm saying about inductive effect, is the pull, right? Yeah, it does just like in summary or what I've been explaining in regards to inductive effect. Inductive effect is just the pull or push, right? Just the pull or push of electron through the sigma bond, just like a way of a curve. Inductive effect is the pull or push of electron through the sigma bond. That's the inductive effect is through the sigma bond. Inductive effect is the pull or push of electron through the sigma bond. And I said that we have two types of inductive effect. We have the positive and the negative, right? I said that the negative inductive effect, they pull electron, that is, they make carbon positive, and also they increases the carbon ability to be easily attacked by electron rich species, which is the nucleophile. While the positive inductive effect, they make carbon to be negative, right? The negative, they make carbon to be positive and make carbon to be easily attacked by the nucleophile, which is electron rich species, right? Then while the positive, they make carbon to be negative and reduces the reactivity of carbon altogether. And I said that the alkyl group, they usually show a positive inductive effect altogether. So in essence now, the inductive effect, right? They help. The inductive effect helps to explain why some organic reaction. That's what I'm trying to say. Factor influencing organic reaction. And is in essence the inductive effect. It helps to explain. You have to explain why some organic reactions are more reactive. That is why some organic molecules are more reactive, while others are more stable and less reactive. That is what the inductive effect, it tries to explain. It helps us to understand why some organic molecules are more reactive and others are less reactive altogether. Now let's move to another very important electronic factor, which is the mesomeric effect. Let's move to the next slide. The mesomeric effect. Now let's talk about the mesomeric effect. Let me change the color of my pen now to a white.
Yeah, the mesomeric effect is another very important electronic factor. Mesomeric, sorry, mesomeric. This is also another important electronic factor that influence organic reactions. The mesomeric effect. The mesomeric effect, right? It occurs when electronegative atom. Please take note of this. The mesomeric effect. Mesomeric. It's being spelled M-E. I don't know what is wrong with my marker. The mesomeric, yeah, effect. The mesomeric effect. It occurs when an electronegative atom. Please take note of this. When an electronegative atom or group is being attached to carbon through a multiple bond. Altogether, when an electronegative atom is being attached to carbon through a multiple bond, that is what we call the double bond, right? There's through a multiple bond, either a double or a triple. Yeah, either a double or a triple bond altogether. And also, when this happens, right? Now let me explain what happens when an electronegative atom or group of atoms is attached to carbon through a multiple bond, either be it a double bond or a triple bond. Is that when this happens, the multiple bond, right? This multiple bond become polar altogether. Yes, the multiple bond, after the electronegative atom is being attached to carbon through a multiple bond, either double, triple bond, right, or etc. The multiple bond, it becomes polar. Altogether. Yes, the multiple bond becomes polar, and also the pi electron. Altogether, the pi electron are pulled towards the more electronegative atom. We are together. Yes, you know what form a double bond? We say is the sigma bond and the pi bond. That's what form the multiple bond, right? That's what form a double bond. Are we together? Now, I said that the multiple bond, either being the double bond, it become electronegative. Are we together? But the pi electron are pulled. That is the electron that is being shared. The bond is what? Electronegative. The bond become polar. Altogether. Then the electron that is being shared is pulled towards the more electronegative atom, not carbon this time around. That's what happened in mesomeric effect. Altogether, the pi electron, they are pulled towards the more electronegative atom. Altogether, they are pulled towards the more electronegative atom. This is what happens after carbon is being bonded by a more electronegative atom. That is the mesomeric effect. It occurs when carbon is being bonded by an electronegative atom. Altogether through a multiple bond. I say what happens after this reaction is that the multiple bond become polar, while the pi electron are pulled towards the more electronegative atom. Altogether. Now, because of this movement of the electron, that is, because of the movement of the pi electron, right, the molecule can no longer be represented by just one structure because the shape will change definitely. Altogether. Then, if you check from this diagram, that's what I'm trying to explain. This diagram. Yeah, I'm trying to explain what happens here in this diagram. We're together, right? Now, as a result of this movement of the electron, right, the molecule can no longer be represented by just one structure because there is the movement of this pi electron towards the electronegative atom. Altogether. Now, because of this movement of this electron, the molecule can no longer be represented by one structure. Instead, we draw different possible structure. That's why you see different structure here. Altogether, that's why we draw different. That's why your outline, you get to find that there are different possible structure for the same molecule. Altogether, there are different possible structure for the same molecule, and these give rise to what we call the resonance structure. Yes, it gives rise to what we call the resonance. Give rise to what we call the resonance structure, which is also called the canonical structure. Yes, which is also called the canonical structure. Yes, the canonical structure is due to the movement of the pi electron towards the more electronegative atom. Because as a result of this movement of this electron towards the more electronegative atom, the molecule can no longer be represented by one structure. Altogether. Now let me just give a simple example to explain to both first what I'm saying. Now, a good example is the carbonyl group, right? Yes, the carbonyl group and the nitrile group. Let me write it. The carbonyl group, the carbonyl group, which is C double bond, right? Yeah. The carbonyl group and the nitrile group, which is C triple bond, right? All right. Now, they are very good example of compound or atom that have the mesomeric effect altogether. And when you draw the structure of this compound, you get to find out that they have different possible structure for the same molecule. And this gives us what we call the resonance. Yes, on the outline here. And a very good example is the carbonyl group and the nitrile group. Now let's move to another important thing from your outline. Let's move to the next slide. Alright, okay. Conjugation. Alright, now let me just explain conjugation in this, right? Now, conjugation happens, right, when pi bonds they are arranged in alternative pattern. I just want to explain all this diagram that is here. Altogether, yes. I just want to explain all the diagram here for better clarity, which is conjugation, because from the outline said that when pi bonds are conjugated. Now, conjugation only happens when a pi bond, please take note of this, conjugation only happens when a pi bond they are arranged in alternative pattern. Altogether, they are arranged in alternative pattern. Because if you check the example they gave from your slide, you get to find out that we have the CH2, right? The CH2 double bond CH, single bond CH, double bond CH. Altogether, if you check from your slide, that is what you will see. And from this system, you get to find out that the electron they are not localized. Please take note of this thing. The electron, if you get to find out from the structure here, you get to find that the electron they are not localized in one bond. Altogether, they are not localized in one bond. The electron they are not localized in one bond. Instead, the pi electron, that is this bond, the pi electron they are delocalized. Altogether, they are delocalized. They spread across the entire chain. Altogether, that is what I want you to get from this example. Is that when it comes to conjugation, right? When it comes to conjugation, what really happens in conjugation is that the pi bond they are arranged in alternating pattern between the carbon atom, like using this example that I gave now from your slide. Altogether, the pi bond they are arranged in alternative pattern, and in such a system, the electron they are localized. The electron they are not localized. Please take note of this. Let me write it out. The electron they are not localized altogether, and also instead this the pi electron they are delocalized. Please take note of this thing. Let me erase the box. I will write it. Instead the pi electron, right, they are delocalized. Please take note of this. I said the electron are not localized in one bond. Instead, the pi electron they are delocalized delocalize and spread, and they spread across the entire chain, and they spread across the entire chain. They are delocalized and they spread across the entire chain. We're together now. Now something very important happens. This means that something very important happens. Are we together? That is the when it comes to the mesomeric effect, it is not limited to just one bond. Please take note of it. When it comes to the mesomeric effect, it is not just limited to just one bond. It's not just limited to just one bond. Altogether, that is, it can be transmitted to the whole conjugated system. Altogether, it can be transmitted to the whole conjugated system. We are together, right? Now, when we draw the resonance, right? When we draw the resonance structure for such system, right, you get to notice something very important. Altogether, that in some of the resonance forms, certain carbon atom, it carries a full positive charge. Altogether, yes, when you draw the resonance of this system, you get to notice something very important. That in some of the resonance forms, you get to find out that, okay, this is example, I show what I'm saying here, right? You get to find out, it's the one back. Okay, resonance is this one. Is explain what I'm saying. You get to find out that certain carbon atoms carries a very full positive charge. Please take note of this thing. It carries a very full positive charge, and since it carries a full positive charge, this positive charge carbon, right? This positive charge carbon atom become electron deficit, so they are easily attacked by electron since they are fully positive, right? The positive charge carbon atom, charge carbon atoms, they become electron deficit. They become electron deficit, that is deficient, right? And since they are electron deficient, so they become easily attacked by electron rich species called the nucleophile, right? They become easily attacked by electron rich species called the nucleophile. And a very important example is the carbonyl group. Yes, and a very important example is the carbonyl group, that is the C double bond O, right? Yes, it's the carbonyl group. They are a very good example. Altogether, they are a very good example explaining what I'm saying. The carbonyl group, because if you check the carbonyl group, due to their mesomeric effect, you get to find out that the carbonyl carbon is always electron deficit. Yes, if you check the carbonyl carbon, you get to find that the carbonyl carbon is always electron deficit. Always. Yes, it's always electron deficit. It also is always electron deficient or deficit. And since it is always electron deficient or deficit, it is strongly attacked by the nucleophile. Yes, that is, they are strongly attacked by electron rich species, which is called the nucleophile, right? Since the carbonyl group, they are always electron deficit, so they are easily attacked by the electron rich group, which is the nucleophile, right? Yes, the nucleophile. An example of the electron rich group include the OH group, which is the alkanoid, the ammonia group, and the ROH group altogether. And also, one important thing I want you guys to note about the mesomeric effect is that the mesomeric effect is also called the conjugative effect. Please don't forget, yes, it is also called the conjugative effect. The mesomeric effect is also called the conjugative effect. So in essence, that is, in simple plain language, the mesomeric effect is just the shifting of electron altogether. Yes, the mesomeric effect is just the shifting of pi electron in the system with multiple bonds. That is what I'm just explaining for a very long time. Altogether, the mesomeric effect is just about the shifting of pi electron
the shifting of pi electron, the shift of pi electron in system with multiple bond, that is the mesomeric effect altogether. And also one other important thing I want you guys to understand is that when conjugation is present, these electrons, they are delocalized across the molecule altogether. That is, the electron, they are not localized in one bond altogether. That is one key thing about the mesomeric effect. The electron, they are delocalized across the molecule. Let me write it. Yeah, they are delocalized across the molecule, and as a result of this delocalization, it leads to what we call the resonance structure. Yes, it leads to what we call the resonance structure. Altogether, it leads to what we call the resonance structure, and this often creates positively charged carbon atoms and making them more reactive altogether. Yes, and since the electron, they are delocalized across the molecule, it leads to the resonance structure, that is making the carbon to be more positive, right? Yeah, making the carbon to be more positive, and since the carbon is more positive, it makes it to be easily attacked by electron rich species, which is the nucleophile altogether. That is what we call the mesomeric effect, which is the shifting of pi electron in the system with multiple bonds, and as a result of the shifting, it makes the carbon group to be electron to be it makes the carbon group to be positively charged. That is, the electron is shifting away from the carbon group, making it to be more positively charged. And as a result of the carbon group being positively charged, it is easily attacked by the electron-rich species called the nucleophile. Alright, now let's move to the next effect, which is the electromeric effect. Now let me wipe my board, then we continue. Alright, the third factor influencing organic reaction, that is under the electronic factor, right? Because we said that it is the factors influencing organic reaction, they are divided into the electronic factor and the steric factor, right? Now also under the electronic factor, the next factor influencing organic chemistry, which is the electromeric effect. Let me write it out. See, the electromeric effect. Alright, now let's talk about the electromeric effect. One thing I want you guys to note about the electromeric effect is that it is very, very, very similar. Okay, it's very, very similar to the mesomeric effect. Yes, it's very, very similar with the mesomeric effect, and mostly students, they often confuse the two, but there is a great difference between the two altogether. Yes, that is one of the confusion I want to clear, is that the electromeric effect is very, very similar to the mesomeric effect, but they are quite different altogether. Now, the electromeric effect is a temporal effect that occur altogether. Please take note of this thing, the word temporal. The mesomeric effect is the temporal effect. Yeah, it's a temporal effect that occur when the pi electron in a multiple bond shifts completely altogether. Yes, the electromeric effect, I said that is very similar to the mesomeric, right? Yes, in the sense that they are very, very similar altogether, because there is a shifting of the pi electron. But in the electromeric effect, there is a temporal effect altogether. It is a temporal effect that occurs when the pi electron in a multiple bond shifts completely. Temporal, when the pi electron in a multiple bond shifts completely, when it shifts completely to one atom, altogether when it shifts completely to one atom in the presence of an attacking agent. Please take note of this. That is, it only occurs during reaction. That is what I want to explain. One key thing I want you guys to take a note about the electromeric effect, that it is a temporal effect, right? Yes. Number one is a temporal effect, and also there is also the shifting of the pi electron in a multiple bond, in which that pi electron is shift completely towards the atom, altogether away from carbon, right, towards an atom in the presence of an attacking agent, that is doing reaction. Yes, doing reaction in the presence of an attacking agent. Attacking agent. Altogether. So in essence now, that is unlike the mesomeric effect, right? You know that the mesomeric effect is permanent. Altogether, that is the key difference between the electromeric and the mesomeric. In mesomeric, the shift is permanent. Altogether, it's a permanent effect, while electromeric effect is a temporal effect when the pi electron in a multiple bond shifts completely to one atom in the presence of attacking agent. But in mesomeric is a permanent, it's permanent altogether. And also one key thing I want you to understand about the electromeric effect is that it occurs during a reaction. That's why I said during, in the presence of an attacking agent, right? Yeah, during a reaction. It occurs during reaction. Yes, it occurs during reaction. And mostly this effect is mostly seen in a conjugated or aromatic system. Yes, as I said, they look similar to the mesomeric. And this effect, that is the electromeric effect, is mostly seen in the likes of aromatic system and conjugated system, like the likes of benzene. Altogether, now let's move to the next slide, so I will explain the example they use here. All right, okay, the next slide. All right, you know, benzene is an aromatic compound, right? Yes. Now let's take benzene to explain electromeric effect as an example, using benzene as an example of an atom with electromeric effect. All right. Now you know benzene, right? Let's use chlorobenzene. From the example they gave from the slide, they use chlorobenzene. We said that electromeric effect is a temporal effect that occurs when the pi electron in a multiple bond shifts completely to one atom in the presence of an attacking agent, that is doing reaction, right? Now you know, in chlorobenzene, right, there is a benzene ring, right? Yes, from the word chloro and benzene, right? Yes, there is a benzene ring, right? Yes, from this structure here, you get to find out that there is a benzene ring with a chlorine, right? Yeah, there's a benzene ring with chlorine. Sorry, there is a benzene ring. There's a benzene ring with chlorine, right? Yes, that benzene ring with chlorine atom attached to it. From this diagram, this is the benzene ring. This is the chlorine atom attached, right? All right. From this first diagram, you get to find out that the chlorine is at position 1. Yes, because if you check in this diagram, you get to find out that the chlorine is at position 1. And the reason why the chlorine is at position 1 is because it is the only substituent. Altogether, yes, you know, chlorine it is the only substituent. That is why chlorine is at position 1. Altogether. Now, I want you guys to go into the journey with me. Now we can look at this benzene ring, right? Yes, we can look at it in 2 directions. Yes, from this diagram now we can look at this benzene ring in 2 directions. That is, we can look at it from the perspective of the clockwise direction. We can look at it from clockwise direction, that is to the right, and also anti-clockwise, that is to the left, right? Yes, we can look at it from 2 directions, to the right and to the left. We're together now. Because of this, different perspective of view that we want to build this chlorobenzene ring, you get to find out that you identify different relative position on the ring. Yes, you get to find out that if you are going clockwise, you get to find out there will be different position on the ring altogether. And also if you are going anti-clockwise or counterclockwise, you get to find out that there is different relative position on the ring altogether. Now position in the benzene. Now the position in the benzene. Now let's start from chlorine at position 1 altogether. Yes, chlorine at position 1. Let's take like the chlorine is at position 1, right? Now the carbon altogether, the carbon next to it on the both side, they are at position 2. Look at it. This they are what at, this is 1, this is 2 altogether. The carbon close next to it, they are what at position 2, and the carbon next is at what position 3. Look at it. This is 1, 2, 3 altogether, and the carbon adjacent to the chlorine is at position 4. Here it is 5 and 6. We are together, right? This is 1, 2, 3, 4. Adjacent to the chlorine is at position 4 altogether. Now the main thing that I want to bring out from this in relation to the position is how to use the right name altogether. Now for instance, now the carbon next to, that is next to the chlorine, that is next to the chlorine, that is at position 1. If you want to name it, you use the word auto. That is what I want to bring out, the name, how to name it altogether. Use the word auto position altogether, which represent the carbon is at position 2. When you read the word auto, when it comes to objective question altogether, they might say carbon is in auto position. What should just come to your mind is that carbon is at position 2. We are together, right? Now when you hear the word metal, because of objective question, that's what I'm bringing out, you get to what should come to your mind, that carbon is at position 3 altogether. Then when you hear the word para, yes, para position, that is carbon is opposite to the chlorine or is opposite to the substituent altogether. Yes, para position 3, right? Yeah, carbon is opposite the substituent when you hear the word para altogether. So in exchange, in summary, that in exchange, electromeric effect is just a temporal shifting of the pi electron altogether. And also one important thing is that it only happens when a reagent approaches the molecule that is doing reaction altogether, and it differs from the mesomeric effect in the sense that its effect is not permanent, unlike the mesomeric effect that its effect is permanent altogether. Yes, now let's move to what we have next on our slide. Alright, now the next thing on our slide here is isomerism. Now let's talk about, let me write it out, isomerism. Let me use my white pen. Isomerism. Right now let's talk about something different. Alright, now isomerism from a slide. Isomerism is the existence of different compounds, right, that have the same molecular formula. Yes, the same molecular formula, but different structural arrangements. Altogether. Now in exchange, just in simple words, isomerism compound with the same word molecular formula altogether. Yes, they have the same molecular formula, right? Different structural arrangements, that is different structure, and also since they have different structure, therefore their property will be different. So therefore they also have different property. So therefore isomerism is the existence of compound with the same molecular formula, different structure, and different property altogether. Now isomerism is broadly divided into two. Let me wipe my board. We have the structural isomerism, and the stereoisomerism. I said that isomerism is broadly divided into two main types, which is the structural isomerism and the stereoisomerism. For the structural isomerism, it's just a type of isomerism that arises. Let me write it. The structural isomerism. The type of isomerism that arises from differences in structural formula. Please take note of this. There are this type of isomerism that occur as a result of differences in the structural formula. That is, meaning the way the atoms are connected, right? Yes, the way the atom they are bonded. That is their structure. Altogether, yes. This is the type of isomerism that arises due to differences. Please take note. The structural isomerism. This is the type of isomerism that occurs due to differences in structural formula. That is the way a molecule and atom is being bonded, right? That is the structural isomerism, and they include, from your outline here, we have the chain isomerism. They include the chain isomerism, the positional isomerism, and functional isomerism. I said that for the structural isomerism, the type of isomerism that arise from differences in the structural formula. That is the way the atoms are being bonded, right? Now let's move to the first type of structural isomerism, which is the chain isomerism. The chain isomerism. Alright, let's move to the next slide. So we'll be on the same page. Alright, for the chain isomerism, the isomer, right? Let me just give the key differences because they all look similar. Like in the chain isomerism, right? The isomers, they have different carbon chain arrangement. That is all. Altogether, yes, they just have different chain isomerism. In the chain isomerism, the isomer, they have different carbon chain arrangement. Different from the one chain, right? Different carbon chain arrangements. Yes, they have different carbon chain arrangement. That is, they have the same molecular formula. Please take note of this. In the chain isomerism, the atom, they have the same, or the compound, they have the same molecular formula, the same functional group. They have the same molecular formula, the same functional group, and they belong to the same homologous series. Altogether, they belong to the same homologous series, but they have different carbon chain arrangements. Altogether, that is what the chain isomerism is talking about. Altogether, they have different carbon chain, but they possess the same functional group, the same molecular formula, and they belong to the same homologous series. Alright, now let me just explain this chain isomerism. Alright, now using, what will I use now? Which illustration will I use to explain this so that it will be more graphical? Alright, now if the illustration come, I will come back to it. Now from our outline here, the example that they use as an example of chain isomer, they use butane. Yes, C4, right? The fourth organic compound, right? Yeah, butane. They use butane. You know that butane has, which is CH4, right? C4 8 what? 4 times 2, 8 plus 2 pen, right? C4 H10. Alright, now when it comes to butane, right, we can write butane in two ways. Let me just use it to explain what chain isomerism is. we said that in chain isomerism or chain isomer, they have the same functional group, the same homologous series, but they have different carbon chain arrangement. Now, using butane as an example, we can arrange butane in two ways, right? Please take note of it. We can arrange butane in two ways using the straight chain. Yeah, we can arrange butane in two ways using the straight chain, which will be a C, right? Single bond, another C, something like this. Yes, you can arrange butane in three ways. You can arrange butane in two ways, something like this. Yes, this is the straight chain butane. The straight chain butane. This is the straight chain butane, and also that is in its condensed form, it will be like the CH2, right? CH3, CH2, CH2, CH3. Altogether, yeah, it can be written in two ways, which is the straight chain butane and the branch chain butane. Yes, just to illustrate what a chain isomer is. Altogether, they have the same molecular formula, the same functional group, and they belong to the same homologous series, but they have different carbon chain arrangement. Like this is the branch chain butane. It will be like this. This is your parent carbon, CH, CH, right, and CH3, CH3, CH3. Yeah. Let me place it at carbon number 2. At carbon number 2. Yeah, let me place it at carbon number 2. Yes, CH3, right? And let's condense it, CH3. You know now the name have changed, right? Yes, it's no longer a normal butane. Now then let me clean the bond, so I will expand it properly. Alright, let me expand it properly. You know, it will be something like this. Yes, let's see. Yeah, let's see. No carbon is tetravalent. No carbon is tetravalent, right? Now you know now that the name have changed now. The branch structure of the normal butane. Now it's no longer N-butane. Altogether, it's no longer normal butane. Now it will be, if you put it at the lowest, the substituent with the lowest number as possible to be 2, right? It will be now 2-methyl propane. Altogether, now what you see here is that they have the same molecular formula, which is what CH4H10. Altogether, yes, both the straight and the branch, they have the same molecular formula. They belong to the same homologous series, but they have different carbon skeleton. Altogether, now the only difference is just in the carbon chain. Altogether, which is either straight or branch. Alright, now let's move to the second type of structural isomerism, which is the positional isomerism. Positional isomerism. Positional isomer. Alright, now here in the positional isomerism, the carbon skeletons, please take note of this. In the positional isomerism, the carbon skeleton is the same. Yes, the carbon skeleton, they are the same, but the position of the functional group is different. Yes, the position of the functional group is different. Position of the functional group is different. Altogether, yes, the carbon skeleton is the same, but the position of the functional group differs. Altogether, so therefore, these isomers, they are chemically similar. The reason why they are chemically similar is because they have the same functional group. Let me write it. Let me wipe my board so I'll write what I'm saying now. Yeah, I said that these isomers, they are chemically similar. Yeah, the reason why they are chemically similar is because they have the same functional group. They are chemically similar. They are chemically similar because they have the same functional group. Because they have the same functional. They have the same functional group altogether. But yeah, the carbon chain is the same altogether. But the only thing here is that despite they have the same functional group, the carbon chain, the carbon chain, sorry, the carbon chain is the same. But the only difference here is that the position of the carbon chain changes. Sorry, the position of the functional group changes. That is very different. And despite the position of the functional group changing, they still have the same. Their chemical property is still similar. The reason why the chemical property is still similar is because they have the same functional group, but the position of the functional group the position of the functional group changes. Position of the functional group changes together, right? Now, okay, let me use the example from the slide to explain the positional isomer. They use propanol. All right, propanol has the molecular formula. Propanol, it has a molecular formula of CH3. Sorry, okay, yes, molecular formula of C3 H 3 times 2 6 plus 2 8 and OH attached to it, right? Alright, yes, C3 let me break it, propanol with the OH attached to it. Yes, with the OH attached to it. 1 2 3 4 5 6 7 and 8 with OH attached to it. Sorry, 1 2 3 4 5 6 7 8. Sorry, yeah, it has the molecular formula of CH3. Sorry, mistake, CH3 H8 and O. Yeah, or I can write CH3 H7 and OH. It is still the same thing, right? Propanol, it has the molecular formula of C3 H8 and O. Alright, now to explain the positional isomer, right? Now at position 1 altogether, that is the OH is the functional group. We said that in positional isomer, right, they have the same molecular formula altogether. Yes, they have the same molecular formula. They have the same molecular formula, but the only thing here is that they have the same molecular formula. The carbon skeleton is the same, right? But the only thing here is that the position of the functional group it changes altogether. Despite the position of the functional group changes, they still have their chemical property is still similar. The reason why their chemical property is still similar despite the position is because they have the same functional group, right? Look at it here, the same functional group, the carbon change are the same, but the position changes, right? Now at position 1, this is the functional group, right? At position 1, it's named propanol, right, which is the normal propanol, N propanol, right? Now let's place the functional group at position 2. It will check at position 2. This is at position 1. At position 2, it will be something like this: CH3, right? CH, right? And CH3. Then let's place it here, something like this. Now there is a little change, right? Despite the structure is the same altogether. Yes, the structure is still the same. This is the parent chain altogether. Yeah, this is the parent chain, but the only difference here is thus the position of the functional group. But we check here, the structure is same. The structure is the same. Yes, the structure is the same. If I expand, you get to understand the structure is same. The structure is the same. Is the C.
The structure is the same, but the only thing is just the position of the functional group. Yes, the structure is still the same. Just the position of the functional group at position 2. Altogether, the structure is the same here. The functional group is the same, but the only difference is just the position. Altogether, and the difference is just where this OH is being located, right? Yeah, that is the only difference. Altogether, right? That's what we call the functional isomerism. You know, now this one, now the name will change to propan 2O. When we come to naming of organic chemistry, when we go when we dive deeper, yes, I will teach you guys how to name organic compound. You know, now because of the change of the position, the name changes from propanol or propan 1 or to propan 2 oil because of the position of the functional group. That's better, right? Now let's move to the next type of structural isomerism, is the functional group isomerism. Alright, let me wipe my board, then we'll continue. Alright, the functional group isomerism or isomers. The functional group isomerism. Now this is where it gets very interesting. And in this type of isomer, they have the same molecular formula. Altogether, yes, with all isomer they have the same molecular formula. General characteristic of isomer, they have the same molecular formula, but this will get interesting, but different. Altogether, different functional group entirely. Yes, different functional group. Yes, they have the same molecular formula but different functional group. Now let's use the example of the alcohol group, right? Yeah, which is let's use butanol something. Okay, let's use this molecular formula C2H6 and O. Right now, with this functional group, let's see from the example from the slide here, CH3, right? CH3, CH2 and OH. You know, this represent the alcohol because of the OH functional group, which is the alcohol, right? Now if it's like something like the CH3O and CH3, you know, this represent the ester. Yeah, the ester group. Altogether, this represent the ester group. Altogether, because we get to find out the O represent the ethyl group, right? While the OH represent the alcohol group. Altogether, and since they have different functional groups, so therefore they behave completely different. Yes, they behave completely different. Altogether, they do not have similar chemical property. They are completely different. Altogether, that is the functional isomerism. Now also there is also another type, yes, from which you slide D, which is the tautomerism. Yeah, tautomerism. The tautomerism, this is just a special type of isomerism. Altogether, it's just a special type of isomerism. Here is that two isomeric forms, they exist in dynamic equilibrium. As I said, a special type of isomerism. Here, two isomer, right? Yes, two isomeric form, two isomer, they exist in the same, they exist in a dynamic equilibrium. That is what happened here. They exist in a dynamic equilibrium. Yes, they exist in dynamic equilibrium. Altogether, yes, that is, and in essence they can be interconverted easily, and they can change position easily. Altogether, and a very good example from our slide here is the ketoenol tautomerism. Yes, the ketoenol tautomerism. Let me write the enol. Yeah, the keto-enol tautomerism, it's that is the aldehyde and the ketone, right? Yeah, keto-enol tautomerism, the aldehyde and the ketone. The aldehyde and the ketone, they are the common example of the keto-enol tautomerism altogether. That is, one form is the ketone form, right? Yes, one form is the ketone form. Let me clean my voice. I will explain. Yeah, one form. I said that one form, that is, there exist two isomeric form, right? Two isomeric form, they exist in dynamic equilibrium. That is what is happening in the tautomerism altogether. Yeah, and the example for my slide here is they use the keto-enol. Yeah, the keto-enol tautomerism. You know, the keto-enol tautomerism is seen mostly in the aldehyde. Yes, it's seen mostly in aldehyde and ketone. In aldehyde and ketone, that is, one form is the ketone form, right? Yes, one form is the ketone form, which is the CH3. Yeah, ketone and CO, right? CO and a C3. You know, ketone, these guys look like this is the functional group. CO, something like this is the ketone, right? The other end, which is the enol form. Yeah, this is the enol form, which is a CH3. You know, enol, they have double bond, right? Double bond C O, yes, OH. This is the enol form 3, right? Yeah, that is a common example of the ketonol is the aldehyde and the ketone. One form is the ketone, and then the other is the enol, right? Which is the aldehyde, right? Is the enol form. Now, what is really happening here is that the hydrogen, there is shift altogether. Yeah, the hydrogen, they shift position. Yeah, that's what is happening here. The hydrogen, they shift position altogether. Yeah, they shift position, and also aside from the hydrogen shifting position, what is really happening is that number one, the hydrogen, they shift position. The hydrogen, they shift position. They shift position, and also the double bond. Yes, the double bond also, they also shift position. Yes, the hydrogen, they shift position. Then the double bond, they also, they shift position. That's what is happening here. The hydrogen shift position, then the double bond here also shift position altogether. And both form, they exist. That is, these both form, they exist in dynamic equilibrium. Yes, as the hydrogen is shifting, this other one is also shifting. They just exist in dynamic equilibrium. They exist in dynamic. They exist in dynamic. They exist in dynamic equilibrium altogether. Yes, so they are constantly interchanging. Yes, they are constantly interchanging. That's what's happening in tautomerism altogether. Yes, that's what really happened in tautomerism. It's just a special type of isomerism. Yeah, two isomers, that is, two isomeric form, they exist in dynamic equilibrium altogether. That is, they are actively interchanging. Yes, they are actively interchanging altogether. As the hydrogen bond is shifting position, the double bond also shift position. So they just exist in dynamic equilibrium. We're together, right? Now, so in essence, structural isomerism happens when the compound have the same molecular formula but different structural arrangement. That is, the way the molecule, they are being bonded together. And this type of isomerism, that is structural isomerism, it includes the chain isomerism, which have different carbon chain. The positional isomerism. In positional isomerism, there is different position of the functional group. Then the functional group isomerism, in which it has different functional group. And also the tautomerism, which exists in dynamic equilibrium. That is, there is a dynamic equilibrium between two forms. Alright, now let's move to the next type of isomerism, which is a
isomerism. Now let me wipe my board, then we continue. Alright, the stereoisomerism. The stereoisomerism. Right now let's talk about the stereoisomerism. In stereoisomerism, yeah, the compound have the same functional group. Sorry, they have the same molecular formula. Yes, they have the same molecular formula. They have the same molecular formula, the same structural formula. Altogether, they have the same molecular formula, the same structural formula, but they have different spatial arrangement. That is the way they are being positioned. Altogether, yes, I said that the stereoisomerism, here the compound, they have the same functional group, the same molecular formula, the same molecular functional group, the same molecular formula, the same structural formula, but different spatial arrangement. That is the way they are being positioned. Different spatial arrangement, right? That is the 3D, right? The way they are being positioned. Right together, they have the same molecular formula, the same structural formula, but they differ in their spatial arrangement. That is the way they are being positioned. Right together, right? Yes, that is in essence the same atom, the same connectivity, but different spatial arrangement. Now the stereoisomerism, they are divided into three main types. That is the cis-trans, right, which is the geometric. The cis-trans, which is the geometric. The cis-trans. Let me explain what the cis-trans is. The cis-trans, right, which is also called the geometric. This type of isomerism, it normally happen, or it is restricted to rotation in molecule. Altogether, that is, this type of isomerism, it's normally happen when there is restriction, when there is restricted rotation in molecule. That is what happened in the cis or trans, which is also called the geometric isomerism. This type of isomerism happen when there is restricted rotation. Please take note of this. When there is restricted rotation, when there is restricted rotation in a molecule, when there is restricted rotation in a molecule. Yes, when there is restricted rotation in a molecule, and it is normally seen in double bond, right? Yeah, in double bond, like the likes of the cycloalkane, right? Like the cycloalkane. Now let's move to your next slide. Right now, from this diagram, they make use of butane. Yes, they make use of butane. Yeah, butane. Yes, your butane. That's what they make use of here. From this diagram, you get to understand they make use of butane. Yeah, your butane. Let me explain this diagram properly. Yeah, they make use of butane, right? That is CH4 H8, right? It is your butane. Yeah, butane. You get to understand that they have the same molecular formula, right? The same connectivity, but different arrangement in space. Altogether, yes, different arrangement in space. Now, for instance, I'm using the 6 as an example. We say 6 trans, right? We said they have the same molecular formula, the same molecular formula, the same structural formula or connectivity, but different arrangement. That is, different spatial arrangements. Yeah, but different spatial arrangement. Now for the 6, you get to find out that both similar group, altogether both similar group, they are on the same side. Please take note of it. This is the butane. We have 2 carbon. Yeah, both similar group, they are on the same side. Something like this. Let's get it right. Both similar group,
they are on the same side. This is hydrogen, hydrogen. You get to find out that both similar group, they are on the same side, right? Yeah, that is, you get to find out, you get to find out that the CH3, they are on the same side. The hydrogen atom, they are on the same side. All together, and since they are on the same side, they are more polar, right? Like this one, they are more polar and they are less stable. Since they are more polar, they are less stable. Yeah, they are less stable. They are less stable. All together. Now for the trans, for the trans, for the trans isomer, at least the opposite side, right? Yeah, the group they are in the opposite side. Yeah, they are in opposite side. There's a double bond. They are in opposite side. They are in opposite side. This is my C3. Hydrogen here. Hydrogen here. They are in opposite side, right? Yes. And since they are in opposite side, the methyl group, they are in opposite side, so therefore they are less polar. And since they are less polar, they are more stable. This is one of the characteristic feature of the trans isomer. Altogether, they are less polar, more stable. Yeah, they are less polar, and since they are less polar, so therefore they are more stable. Together, right? Now let's move to the second type of stereoisomerism, which is the conformational isomerism. Let me wipe my board so that I will explain. Alright, the conformational isomerism. The conformational isomerism. The conformational isomerism. This one is very different, right? And this one, it normally happens due to free rotation. Yeah, it normally happens due to free rotation. Due to free rotation around a single carbon to carbon bond. Right? Yeah, the conformational isomerism, it happens due to free rotation, right, around a single carbon to carbon bond. That is, the molecule, they can rotate without breaking bond. Yes, yeah, the molecule, they can rotate freely. They can rotate freely. They can rotate freely without breaking bonds. And this creates different shape, which we call the conformer. Yes, they can rotate freely without breaking bond, and it results to the formation of shape, like different shape, since they can rotate freely. So therefore, as they rotate, they produce different shape. That's what we call the conformer. Altogether, from the name, that's what we have the conformational isomer. The reason why they are called conformational isomer is that they can rotate freely, right, without breaking bond. That is, there is free rotation around the single carbon bond. Alright, now for the example, yeah, okay. Alright, let's use example to explain, like using ethane. Yes, let's use ethane as an example to explain the conformational isomer. Alright, now we can look at ethane, right, in two main forms. Please take a look at this. We can look, in order to explain the conformational isomer, we can look at ethane in two main forms, right? In two main forms. Number one, let's look at it as we can either look at it as an eclipse. Yeah, as an eclipse conformation. That is an unstable, right? Yes, an unstable. The unstable is also called the boat form, as an unstable conformation. right? Just to explain what's happening in this conformation isomer. Alright, we can look the chain in two different forms as an unstable or both form, right? That is eclipse conformation. Here in the eclipse conformation, here the hydrogen, right? The hydrogen they are aligned. Are we together? Yes, they are the hydrogen. The hydrogen they are aligned, and since they are aligned, so therefore there is maximum repulsion. Please take note of it. Since they are aligned, there is maximum repulsion. There is maximum repulsion. Since they are aligned, there is maximum repulsion. All together. Alright, now let me draw this thing. We say we are using it, right, which is CH3, right? Yeah, CH3, right? I said that when we look at a chain from the eclipse, that is, you can look at it in two forms, either in eclipse conformation or stagger conformation. From the eclipse conformation, you get to find out that here the hydrogen they are aligned. Let me draw the structure, you get to understand what I'm saying. The hydrogen they are aligned, and since they are aligned, there is maximum repulsion altogether, and also the bond here they are overlapping. Yes, and since the bond they are overlapping, there is what high repulsion. Yes, there is high chances of repulsion, and also they are less stable. That's the thing I wanted to take note. There is high chances of repulsion, and also they are less stable. Let's get it right. Now, if you look at ethane from the stagger form, that is in the stagger conformation, when it rotates in the stagger formation, that is, it forms a chair. Yes, it forms a chair or it forms a chair. But if you look at it from the eclipse form conformation, it forms a both form, right? Yeah, it forms a both form. Okay, yes, and since it forms a chair, the hydrogen they are far apart together, but in the eclipse conformation of ethane, you get to find that the hydrogen they are very close. That is, they are very aligned, and since they are very aligned, look at it, something like this. They are very close. Right, let me draw this thing properly. They are very close. The hydrogen they are very close, like this hydrogen, and since they are very aligned, they are very close, there is high chances of repulsion, and since there is high chances of repulsion, they are less stable. Let's get it right. Now, why for the stagger conformation? For the stagger conformation, let me erase it for a little. For the stagger conformation, the hydrogen they are apart. I said the stagger, which is also called the chair, right, or the stable conformation, or the stable form. Here the hydrogen they are apart. Altogether, yeah, the hydrogen they are far apart. They are far apart, and since the hydrogen they are far apart, so therefore the bonds they are overlapping. Sorry, no, the bonds are, no, the bonds they are not overlapping. The bonds are overlapping in the eclipse. Yes, in the eclipse the bonds they are overlapping, since they are very aligned, like they are very close to each other. Since they are overlapping, and also there is high repulsion. Since they are overlapping, there is high repulsion, and also they are less stable. Why in the stagger conformation form, here the hydrogen they are far apart, and the bond they are separated. The bonds are separated, and since the bond they are separated, so therefore there is minimal repulsion. Yes, there is minimal repulsion, and since there is minimal repulsion, it is the most stable. Please take note of it. It is the most stable. It is the most stable form. Altogether, yeah, it is the most stable form. It is the most stable form. Right? Yes, it is the most stable form. Look at the structure. It looks something like this. The bond they are far apart. Yeah, it is the most stable form, and it has the minimal repulsion, and the bond they are separated. So in essence,
when it comes to conformational isomerism, they have they are the same molecule, right? Yes, they are just the same molecule, but there's just rotation. There's just rotation around a single bond. And since there is rotation around a single bond, there is also different energy level. That's what the conformational isomerism is talking about. Rotation around a single bond, the same different energy level, right? Different energy level, and also the same molecule, because it's just the same molecule, but there is just rotation around the carbon to carbon single bond. Right, together now. Now let's move to the optical isomerism, which is the last thing we have in this slide. Let me wipe my board. Right, the optical isomerism. Yeah, this one is very important. Right, and the optical isomerism, it normally happens when a compound, right? It normally happens when a compound can rotate, yeah, can rotate a plane polarized light. Yeah, when a compound can rotate a plane polarized light altogether, that is, one form can rotate light to the left. It can either look that in optical isomerism, it just happens when a compound can rotate a plane polarized light, and it can be in two forms altogether. Either it can rotate it to the left, it can rotate it to the left, which is called the level, yeah, which is called the level rotatory, right? And also you can rotate it to the right, which is the dextro rotatory. That is the dextro sorry, don't spell D. The dextro rotatory. Yeah, either the left, which is the level rotatory, or the other, which rotates the light to the right, which is the dextro rotatory. That is, in optical isomerism, it happens when a compound can rotate plane polarized light either to the left, which is the level rotatory, or to the right, which is the dextro rotatory. And we've come to the end of the slide. And in our next video, we'll go into homologous series. Yes, we'll go into deeper into organic chemistry. And please don't forget to like, subscribe, and comment on our YouTube channel if you find this video helpful. See you guys in the next video.